So in this video, we're going to look at the graphs of polynomial functions and see all of the things we can determine about the actual function just from what the graph looks like. And in the next couple of examples, we'll actually be writing the full equation of the polynomial based on the graph. So I chose this question to do first. I obviously screenshotted this from a website, so we're not going to submit it. But it brings up a lot of good vocabulary and lets us analyze the graph and see what we can figure out. So it asks you which of the following are true, which means that a bunch of things in here could be true and some might be false. So we'll start with the first one. It says x minus 3 is a factor. So if that was true, that would mean that x equals 3, positive 3, would be a root. So I'm going to go to my graph. And in fact, I do see that the graph hits the x-axis at 3. So that means this first one is true. I'm just going to kind of put check marks next to the ones that are true. Then it says negative 2 is a root. Okay, well that one's easy. I do not have to change the sign because it's already written like a root or a solution. And so again, if I look over here, I see that the graph hits the x-axis at negative 2, so that's also true. Then it gives us this really weird notation. If I was going to read this, I'd say as x goes to negative infinity, f of x goes to negative infinity. So what does that mean? They're basically saying as x gets really small, because it is saying negative infinity, so to highlight x getting small, I'd be looking towards the left side of the x-axis. And then it says that f of x would also be going to negative infinity. Well, we know f of x is a fancy way of saying y. So they're saying as x gets really small, y should also be getting small. And since the function is actually pointing up on the left side of the graph, that is not true. Okay, so then it says the degree is 3. Well, if that was true, that would mean that this is an odd function. But one of the things I can notice right away is that the ends of this function, like the start and end points, are facing the same direction, which automatically means that this is an even function. So that means that degree cannot be 3. Then it says x minus 0 is a repeated factor. So again, they're giving it to me as a factor, so I would say that would mean that x equals 0 is a solution or a root. And in fact, I do see that it's hitting the x-axis at 0, and it's actually doing what we've been calling in class either a turnaround or like a bounce, which does mean that this is repeated, so that is true. It says there's a maximum at x equals 2. Well, that would basically mean that the graph had a high point at x equals 2. That's really what that means. So if we go over here and look at where x is 2 on the graph, and then I follow down to the actual shape, this would not be considered a maximum because it's definitely like a low point. It's almost like a vertex on a parabola if that parabola opened up. So that's not true. We would actually be able to say that there's a minimum at x equals 2. So this is not going to work. And then finally, we've got more of this funky notation. This is saying that as x goes to infinity, or as x gets really big, f of x, which we know is y, also gets big. And if we look on the right side of this graph, it's true that the function itself is increasing. So that would be a true statement. So we had that the first and second, fifth, and seventh things that were listed here were true about this polynomial based on the graph. So hopefully that gave you a good little overview of some of the notation and vocabulary that's associated with graphs of polynomials. So now why don't we look at one where we're going to actually come up with the entire equation. Okay, so here's a polynomial function that's graphed, and we're going to kind of pick apart all the little things that we can determine about it, just kind of looking at all of the different shapes and behavior that are exhibited. So the first thing I'm going to look at is where the function starts and ends. So this function is starting in what we would call the second quadrant, and it's ending in the fourth. So first off, the fact that they don't end facing the same direction automatically makes this an odd function. And when you have an odd function that starts in 2 and ends in 4, that means basically the function is decreasing from left to right, so that makes this a negative function. That means that when we write our equation, we're going to need to put a minus sign at the very beginning, right in front of our lead coefficient. Okay, so we understand the end behavior. That's what we call those two pieces of information. Now we need to talk about the root behavior. So at each x-intercept, what's happening? So if I look at the first one that I see, moving from left to right, I have what we called earlier, either a turnaround or a bounce, and that indicates a multiplicity of 2. If you remember, multiplicity means just how many times the root occurs. So that means there are actually 2 x equals negative 5. So that appears to be where it's hitting the x-axis. Okay, continuing on to the right, the next time I see it hit the x-axis is right here. That looks like it's at negative 1. and it's just doing a clean, what we would call a pass-through at that point. So that means that there is one, -1. That would be a solution to this function. Continuing on, I see that at +4, I have that weird sort of flattening out. In class, the formal name I gave you guys originally was what we called a saddle point. We came up with some other names for this, a dolphin point, a squiggle point, and whatever you want to call this. Basically, the graph is sort of flattening and then continuing on, which means that it's repeated 3 times. It has a multiplicity of 3. So there are 3 fours that would be solutions to this function. Okay, so now I have everything I need to know. I have the end behavior, and I have all of the solutions to this. Oh, I'm sorry, there's actually one more solution. Oops, sorry. If I continue looking through, I see that we have another, what we called a pass-through at x equals 7. So there's actually, and that actually gives us our 7th answer, which again makes sense because we knew that this was odd. So that does kind of bring that together for us. So now I can build this equation in factored form. I don't technically know what the lead coefficient would be, but I can at least give one example of what this equation could look like. So we always start this by giving some kind of function notation. You could use p of x, r of x, whatever letter you prefer. Remember, we said we need that negative sign at the beginning. And for every one of my solutions, I'm going to build the factor by changing the sign. So if I had -5 as a root, that means the factor is +5, and since there are 2 of them, I square it. Since I have a -1 as a solution, that means my factor would be x plus 1. There's only 1 of them, so I'm going to leave it just to the power of 1. I have x minus 4 as my next factor, since I have a root of +4. There are 3 of them, so I cube it. And finally, I have one solution of +7, which gives me a factor of x minus 7. And again, there's only 1 of them, so I just leave the exponent at 1. And so this would be an example of what this function's equation could be. And I'm done. Okay, so I have one more example of writing the equation in case you just want to try this again. If you're following along in the video, my suggestion would be pause it here, see if you can write this function's equation in factored form, and then come back and see if you got it right as you hear my explanation. So, like last time, the first thing I'm going to hone in on is the end behavior of the tail ends of this function. So this time we are pointing in the same direction, which means right away I know that it's even. And since they're both pointing up, that would imply an even positive function, which means I do not have to put a negative sign at the beginning of my function. Okay, so next I look at the roots. So the first thing I see is that I'm passing through at -3, so that would be my first solution, and there's only 1 of them because it's just a pass-through. If I continue on, I see that I have another solution at +2. This time I see that little turnaround or that bounce on the x-axis, so that means that there are 2 of them. So I have 2 +2's. And then finally I have another pass-through at +5, so there's just 1 +5. Now again, I have 4 total solutions, which makes sense because we originally said that this was an even function. Okay, so writing this out, again, we can use f of x or some other letter. I do not need a negative sign this time, so I can jump right into the factors. So if I get -3 as a root, my factor would be x plus 3, and there's just 1 of them. If I have +2 as a root, I have x minus 2 as a factor, and it repeats twice. And finally, +5 would give me a factor of x minus 5, and there's just 1 of them. So this would be one example of what the equation of this function could be based on the end behavior and the root behavior.